week 6, part 2, except we're going to finish up the slides from last time. So we're going to go here first. And I'm going to actually start by reviewing a little bit of what we did last time. I was originally planning on going over the midterm today too, but I think I'm going to push that off until next week. Probably here on the lab day, I'll review the midterm first and then we'll have the lab. Just because I know a lot of you are needing a little bit more time, so we'll just wait until next week to do that. So that means, because I had sort of budgeted time for that, we may end up finishing early today. I don't think so, because that tends to not be what happens with me. but we'll see. All right, let me just get fully set up here. Okay, so, oops, no, that's not what I want to do, because I already got it open. All right, so I wanted to kind of start here again, which is when to write a function. So we talked about this last time, but this is just a quick example where we have a data frame that just has some numbers, right? And so in this case, maybe we want to rescale those values somehow, right? And so I've done this like 0-1 transformation, but you could just as easily do z-scores, right? Or whatever. And so if we wanted to do it for one column, we'd probably just do mutate and then redefine A and write all the code that we need to do the transformation there, right? But if we wanted to do it for all of them, then our code starts to get a little bit verbose, right? And so there's nothing that is like inherently wrong about this approach. It's just less than ideal. And it's less than ideal for a couple of reasons. One, we're repeating ourselves a bunch, right? So the way that we're probably actually creating this is we're copying A, and then we paste it again for B, and then paste it again for C, and then paste it again for D. And when you do that, you know, generally that's going to work fine, but when I'm redefining C here, maybe I put C here, C here, C here, but then I forget on this one, and this one stays at B, right? So if that's the case, then C is going to end up wrong. And so we end up with errors in our code that are just introduced by this repetitiveness and this lots of copying and pasting, and even spotting those errors is going to be pretty tricky because it's all sort of jumbled within this big block of code, right? So one thing we could do without writing a function, we actually technically are writing a function here. It's just an anonymous function. And we're doing an anonymous function through per's what's called lambda syntax, this sort of shortcut syntax, right? So we have a tilde, and then we just put a .x in place of each of those. And we can call mapdf here because we're looping through the data frame, where the data frame is a list, and so we're looping through each element of the list, and we're applying this function, right? This anonymous function, which is through per. Alternatively, we could write a function and we could bind that function to a name. Okay, so I asked before, what would the body be and what would the arguments be? And the body is just going to be this part, right? It's just the same thing that we were copying and pasting over and over again. All we're going to do is, instead of having A and B and C here, we're just going to put X, right? And so X is just some generic vector. And we wouldn't have to do X, right? We could do V for vector. We could say vector. We could do whatever, anything we want to do, right? It's just a placeholder argument. Generally, as a rule, X is used to mean a vector, right? But it doesn't always necessarily have to be. So there's the body of the function. And then when we create the function, all we do is we create a name for the function, and then we say function, and then we have the formal arguments to the function here, okay? And then we have our curly braces, and the body of our function goes between those curly braces, okay? Occasionally, you may see people write functions where it's like all in one line. So it'll be like function x, mean of x, comma, na.rm equals true, right? So it's just a little function that sets the mean to remove missing data by default. In that case, you don't technically even need these curly braces, but generally I think it's good practice to do that. Okay, so in this case now, with this function, the body of the function is just the thing that we were copying and pasting a bunch of times. And then we say we have one formal argument x, and that x gets inserted wherever the a and b were, and c. Okay? So then we can test it out. We want to generally test it on cases where we know what we would expect the outcome would be. So here I just have a vector that's 0, 5, and 10. So if I'm going to rescale that to span from 0 to 1, I would expect 0, 0.5, and 1. That's what I get. Here, a sequence from 0 to 100 by 10, and you can see I get 0.1, 0.2, 0.3, right? Again, that's the output we would expect if we're rescaling this thing to be between 0 and 1. Okay? Okay, now again, that by itself is a pretty big step forward, I would argue, in terms of clarity. And not just clarity, but also the likelihood of bugs being introduced in your code, right? It's going to reduce that likelihood by quite a bit, because now you're just calling a function each time rather than copying and pasting a bunch of code. Okay, but if we look at that function, we could still make it easier to read. A couple things we could do in this case. We could remove missing data once rather than doing it every time we're making a calculation. And we could, anytime we're using the same sort of calculation, we should just use that calculation rather than actually calculating it each time. Okay, so here's a little bit cleaned up version where this first part looks the same, except now I'm calling it rescale 01b. And the first thing I'm going to do is create an object in the body of my function, which is called z. And z is just going to be x with missing data removed. Okay, so now when I'm calling min and max, I don't have to use na.rm every single time, right? Then I can just calculate the min of z and the min of and the max of z, the min and max of z, and then I just put it all together down here. So you can see this is like some basically preparatory work, and then this is really the body of this whole thing is the body of the function, but this is like the heart of the function, right? This is what it's doing right here. And so that's sort of easier to read. It's easier to understand what's happening here than this, right? Because this has a bunch of code in it that sort of takes away from what is actually happening there. Okay? In this case, again, it's really not that big of a deal, but this is clearer. And so if you come back 6 months from now, again, like after you get a revise and resubmit, then you'll have this function and it'll be pretty clear what it's doing, versus the other one, you might have to kind of walk through it a little bit to remind yourself of what it's doing. And again, this function is so simple that it's really not that big of a deal. But as your functions get more and more complicated, this sort of thing becomes more and more important, because you want to be able to understand what's happening in your functions, right? So we can test it again, doing the same tests we did before, and just like we would expect, probably we get the same exact results. We can use this identical function to actually test it against 2 different versions, and we can see that the result is true, so those are identical. And then here I'm creating a random vector, and then I'm rescaling 0, 1 on rand and rescale 0, 1b on rand, and you can see that they are also identical. Okay? So, as a final solution, rather than that repeated copy and paste a bunch of times, we could use modify, or we could use mapdf to loop through df and then apply this function rescale 0, 1b. And in this case now, all of that code that we had is reduced to a function and then this line of code. Okay, and so it's more clear what's happening. It's much less error prone, and this is really what functional programming is about. figuring out the problem for one, and then writing a function to solve that problem and iterating it across the whole. Okay? Questions on any of that?
I have a quick question regarding the functions. I realized you didn't use the return command. However, it still returned the numbers. Is there is
Yes.
it the default? Yeah.
Yes, we will actually talk about that today, about return values today. That's one of the topics. But just as a real quick preview, if you put something down here, whatever the last thing is that the function evaluates, that's what it will return. And actually, best practice is to not use the return argument function unless you're having the function exit early.
Oh, okay, thank you.
So I'll talk about that more later today too, though. Okay, any other questions? Okay, so that part is mostly review. Getting a little more complex, what if we want the function to behave differently depending on the input? Okay, then we need to add conditions. And this is the basic structure, right? We have some function that we're defining here, and then we have some condition. And so we say if condition, so if the condition is met, then do all this stuff in between these curly braces. Okay? Else, meaning otherwise, anything else, do this. Okay? There are times when you might want to have just an if condition and then omit the else and you just continue on. And what that's going to do is, as the function is evaluating, if that condition is met, it'll do some additional thing maybe, right? And then it's just going to continue on. So for example, this is like a small example, but it works, right? Like maybe you have an na.rm equals true argument, right? Then you could say if na.rm, meaning if that argument is set to true, then you would na.omit the thing here. And then you would just continue on, because from there on, then you can assume that there's missing data, so you wouldn't need to do an else in that case. You would just do the if. Okay? Other times, you might have an else if. So you have an if, else if, else if, else, or something like that, right? And so this is how you're going to basically check for things and have your function either do different things or even output different things depending on what the arguments to the function are. So again, a really basic example, you could have something where it's like as Tibble, right? And so if as Tibble is set to true, then it's going to return a Tibble. Otherwise, it's going to return a regular data frame, right? Something like that. Okay, here's the else if condition that I mentioned. So if you have lots of things, you define your function here, and then you'd say, if this condition is true, then do this. Otherwise, if this condition is true, then do that. If neither of these conditions are true, then do something else. Okay, and this like structure here, like I think it makes logical sense a lot of the time, but when you come to actually write the code, it's like, wait a minute, where does this else go? Where does the else if go? Is it else if all one word, or etc., right? So I would recommend just kind of keeping these slides as reference for you, because when you get to the point where you're needing to write this kind of stuff, this is the basic template that you'll use. Okay? Okay, so here's an easy example where I'm saying, given a vector, return the mean if that vector is numeric and null otherwise. So in this case, I do have a explicit return. And again, I'm going to talk about this more later, but that's because I'm returning within this else. So by default, it's going to do the last thing that is evaluated, which is down here, which is nothing. And nothing is different than null. If we just say return, it will return null. Okay? So here I have mean2, and I'm saying this is a function that takes one argument, x. Okay? And then my first condition is to test if x is numeric. Okay, so if is dot numeric x. If this function here returns true, then I'm going to compute the mean of x. Else, meaning otherwise, if that's not true, we're just going to return. Okay, and the examples I showed you before had else up here. That's probably actually how I would write it. I don't know why this ended up down a line, but it will work either way. But generally, I would have this on this line up above. Okay, so now we can test it out. We say mean 2 on R norm 12, and we get some mean, right? And then I say mean 2 on letters 1 through 5, and I get null. Okay, because letters 1 through 5 is just A, B, C, D, E, whatever. And so that's not numeric, so it skips over this part because this is false. So it skips that, and then it goes to this else, which is just return. Okay, does that make sense? This is actually mostly what the topic is for today, is conditions. So let's say we wanted to write a function then that returned the mean for all numeric columns in a data frame. Okay, so we wrote this function, and what we're going to do is we're going to use this function that we wrote within this larger function, which I'm calling means df. Okay, so this is a very, very, very common approach, and actually is best practice is to write a bunch of different functions, and I'll talk more about why that is next week, I think. Okay, but this function is going to take one formal argument, df, meaning the data frame, and the first thing we're going to do is we're going to compute the means. So I'm going to say map through the df, through the data frame, and apply that function mean2. Okay, so that's going to give me the means for all the numeric columns, and if they're not mean, or if they're not numeric, then it'll return null. So then in this next line, I'm saying which ones are null. Okay, so I'm saying map LGL, map logical, map through this means list, and apply the function is.null. And because I'm using map LGL, right, that's going to give me a logical vector, atomic vector in return. And it'll be just true, true, false, true, whatever, right? And it'll be true for the ones where it's not null, and it'll be false for the ones where it is, or no, other way around. It'll be true if it is null, it'll be false if it's not null. Okay? Then I'm just going to subset that list. So I have this means list. I'm just going to subset that where I'm saying, give me the means where it's not null. Okay, so nulls is an atomic vector where each element is a true if it's null and it's a false if it's not null. So I'm using the exclamation point here to reverse that. So I'm saying, give me the not null values. Okay, so this will be all the means for the columns that are numeric, basically, right? And then finally, I'm just going to wrap that list into a data frame because that is easy, right? Lists can be converted to data frames as long as the number is the same in each one, and it would be in this case, just be 1. So we can test it out. Here's iris data set, right? These are all numeric, but then species is not. Okay, so I can call means df on iris, and you can see I get a data frame in return that has the means for all the columns except species. Make sense? We do have a bit of a problem though. Okay, here's the air quality data set, and it has missing values. When I call means df on air quality, you can see I get NA for ozone and NA for solar.r. So why is this happening, and how can we fix it? Any thoughts?
Handle the missing data?
Yes. Where, though, specifically?
In the means2 function?
In the means2 function, right? So it's not actually here. It would be back here, right? Here's the mean part, okay? So one way we can do this is to pass the dots, okay? So you have probably seen multiple times when you're looking at the help documentation, this ... argument, okay? That ... argument says anything else, okay? And it can be used for all sorts of different things, but the most common way it's used is to pass additional arguments to functions, okay? So with means2, I'm saying function x ... and then I just put that ... down here. Now, when I call mean2, any argument that can be passed to mean, I can pass to mean2. Okay? Those arguments we can supply here, and it will just pass them down to here. Okay? So now, when I rewrite my means_df function, I pass the dots again. I say df ... and then I'm going to pass those ... as additional arguments to mean2. Okay? If I were to write up the documentation for this function, when I'm documenting that ... I would say additional arguments to mean, and then I would link to the base mean function. And then somebody could go and look at the base mean function and see all the additional arguments they could potentially pass to it. Okay? So now, if I say means_df on air quality, I get the NAs, but if I say na.rm equals true, now it works. Okay? Questions on any of that? Okay. So moving on today, we're going to continue to talk about functions. As I mentioned, I was hoping to review the midterm today, but instead we'll just do that on Monday. So that gives everybody a little bit more time to get that finished up, and then we can hopefully have more of a discussion as a class on it. So then from here, we're going to talk about purity fairly quickly. I don't think it's the most important topic for most of the stuff that we do, but it is important, sort of. And then we'll talk about conditionals some more, so if condition, whatever. And specifically what we'll talk about mostly today is embedding warnings, messages, and errors, okay? And then we will talk about return values near the end, okay? And there will be a couple of times here where I'm going to ask you to try things, little challenges, okay? So if you don't already, go ahead and get RStudio going. Okay, so the learning objectives for this lecture: understand the concept of purity and why it's often desirable, not always, and be able to define a side effect. Okay, so a pure function has no side effects. Well, what is a side effect? All right, we'll talk about that. And then hopefully by the end you feel more comfortable with the idea, even if you, again, like, you know, everything, even if you're not super confident about like just doing it fluently, hopefully you understand the idea of how you would change the behavior of a function based on its input. Okay, so if it's numeric, maybe you do one thing. If it's not, you do something else. If this argument in your function is true, you do one thing. If it's false, you do something else, etc. Okay, and then be able to embed warnings, messages, and errors. Okay, purity. So a function is pure if and only if its output, the thing it's returning, depends only on its inputs. Okay? So the thing that it returns depends only on the things that you feed it. Okay? So what does that mean immediately? It means it can't depend on anything that's in your global workspace. Okay? The other thing is it makes no changes to the world. Okay? And this is like very vague, but what I mean by that is it doesn't change settings in RStudio. It doesn't install something on your computer. It doesn't, it doesn't do anything out there. Like, it doesn't change anything anywhere. Okay, so it takes some input and it returns some output. That output depends only on the input and nothing else, right? And then with that output itself does not alter the state of things in your environment. Okay, that is the definition of a pure function. So any behavior that changes the state of the world, basically any behavior that makes a function not pure is referred to as a side effect. Okay, so again, this is like confusing because there's lots of times we want to do things like change the state of the world, right? We want to install something on our computer. Well, if you're installing something on your computer, that is technically a side effect, right? So if you're installing a new package, that's a side effect because it has changed the settings of, it's changed something on your computer. Okay, so state of the world is not some technical term or whatever. It's just the way that I kind of think about this. All right, so common side effects. We have, I just mentioned one, right? Well, I basically mentioned one. What is that? What's that one I basically mentioned?
Install packages.
Install.packages, yes. Can you think of other potential functions that have side effects that are desirable? Side effects like where you're running a function because you want the side effect.
Library?
Library, yes, absolutely. Because when you run library, all sorts of functions are now available to you that were not previously. So it's binding a new namespace in your global environment, basically, not your global environment, but your workspace. A couple other examples, so library and install.packages. There's also options, right? So options is a global function that you can do things like change the number of digits that are printed, right? Or all sorts of other things. Sys.time, this one is a side effect, but it's slightly different than other side effects because when we're doing sys.time, there's a little girl back there. When we do sys.time, the output doesn't depend, or it changes every time, right? Because the input is like the global time. So it doesn't depend just on the things that you feed it, right? It's going to give you the system time, which is going to change all the time. Every time you run that function, it will give you a different output. So that function is not pure, okay? Read.csv, write.csv, and then these ones are a little bit less clear, but they are also side effects, right? So print will print things to your console. That's a side effect, right? Plot, also creating a plot, right? It's going to basically use some other device to render a plot. That's a side effect, okay? Anything that produces a side effect makes that function not pure, okay? And so there are reasons that you want to generally try to make your function pure, but then there are other times, like with print and plot and write.csv, like all of these, where you're running the function primarily because of the side effect, if not entirely because of the side effect, okay? So when we're thinking about side effects, like generally, if we think about it in like the medical term, medical way, right? It usually refers to some like undesirable thing associated with something, right? Like the side effect of vaccine is you might feel crappy for a day or two, right? But this in programming, side effects are very often desirable. They're really why you're running the function. But that makes them not pure. Okay? So just to review real quick here. Purity is generally something you do want to shoot for. You don't want your functions to change the output that they're giving based on the same input. So if you give it the same input, you should expect the same output every time, right? And that's why things like sys.time is not pure, right? But And then you generally don't want your functions to depend on other things. So it shouldn't depend on something that's in your global workspace. But that's also, that view is much more of a if you're developing a function that's going to be in a package that other people are going to use. If you are writing a function that's just for you and you're going to use it this one time and never again, then don't worry about purity at all. Okay? All right. So that's basically all I wanted to say on purity. Are there questions on that? All right. So conditionals. This is where we're going to start with one of the challenges. This is from an old lab. So I cut one of the labs this term. And this was one of the questions from the lab. Okay. Write a function that takes two vectors of the same length and returns the total number of instances where the value is NA for both vectors. So for example, here, this is 1 and NA, so it should return false. NA 3, no. NA, yes, right? It's NA for both of them here. 3, 4, no. 3 NA, no. 9 NA, no. NA, yes. Okay, so you have these two vectors. The function should return 2 here because it's NA in for both of them in the 3rd and 7th location. Okay, so I'm not going to worry about this part so much. So let's say we had an example like this, and we knew that this is something general that we wanted to do over and over and over again, because whatever our use case is, this is just something where we're going to be basically saying like, okay, we're going to read in some data, and then we're going to check across these columns. And if it's NA for all of those columns, then we're just going to drop that row, right? Or something like that. But if it's not, if there's a value anywhere in there, then we're going to keep it. Okay? So that's like the case that we want to do. So now we want to write a function to solve this problem. And in this case, we're kind of taking one additional step where we're saying sum that now. Tell me how many times we have NA for both of these vectors. Okay? How would we actually start to write a function to solve this problem? Any ideas? Not by writing a function. Okay? We're going to write a function eventually, but if we're going to solve this problem, what we want to do is figure it out on a test case. Okay? So we have these two vectors. We're going to figure out how we would do that for those two vectors. Once we have that, then we can generalize it to a function. Okay? But we're going to solve it first, and then we're going to sort of abstract it away from there to get a function. So use the vectors to solve. All right, so what I'm asking you to do here is you can copy this code, take A and B, and don't write a function, but just try to write code that will count when they're NA for both of them. Okay, so I'm going to give you 3 minutes here. And basically, when the end result here should be 2. Okay, so go ahead and give that a try. See if you can figure out a solution. All right, good job. This is how I would do it, right? So I said is.na for A, and that gives me a logical vector. Is.na for B, that gives me a logical vector. And so what I'm going to do is just say is.na for A and is.na for B. And then I get this, okay? And then the final step is just to then sum that. And when we sum, right, these logicals are being coerced to numeric, where falses are going to 0 and trues are going to 1. So we end up with 2. Is that how you did it? Did anybody else have a different solution?
I had a different solution, and now I'm wondering if it's doing the same thing or not. But I did sum is.na A or B.
Oh, okay. Yeah, that should work too. Wait, A or B? Did you get 2?
Yep, I still got 2.
Yeah, I think that works. I just have to think why. A or B. Oh, right. Yes, it's because you're saying A or B for each of these is NA. I don't know. I'd have to think through that a little bit. I thought I had it, but now I'm not sure I do. But if it works, great. I think it is because of something to do with this. I'd have to work through that again, but yes. But if it works, great. Okay, so now we would generalize this to a function. Okay, this is how I did it. I'm calling this function both NA. Okay, then we say function, it's going to take 2 arguments, x and y, right, are 2 vectors. And we could call it A and B if we wanted to, it doesn't matter. Curly braces, and then for the body of our function, we're just going to put what we had before, what we figured out for those 2 vectors. That becomes the body of our function, and we just replace A and B with x and y. Okay? Now, this function works great for our use case, but what happens if the vectors x and y are not the same length? Well, we can test it out. We can say both NA for A and B, and we get 2. That's great. Both NA for AA and BB, and we get 4. That makes sense, right? Because we're just, this vector is A repeated twice, and this vector is B repeated twice, so we would expect 2 and 2, which is 4. And then in this case, we're now finally feeding it a different length vector. So this is just A, and then this is B and B. And we get 4, right? So we don't have, it's not an error, right? It didn't complain one bit. It just gave us 4. Why did it give us 4? Any idea what's going on here? This is a perfect example of really unexpected results and a really gnarly problem, because if you don't understand what's going on here, then you can end up with results where it doesn't even complain one iota. It's like, yep, this is totally fine. This is 4. And it doesn't give you a warning. It doesn't give you an error. It doesn't give you anything, right? It just gives you a result. But that result is not right? That's not what we would expect. What's going on here is recycling. Okay, and this is a base R sort of property. So R will recycle vectors if they are divisible. Okay, so here's an example where I have the numbers 1 to 4, and then for let's I just have A and B. So this is length 2, this is length 4. I can recycle these 2 letters, and it'll be the same length as nums. And that's what it ends up doing by default without complaining at all. Okay, so we get 1, 2, 3, 4, and we get AB, AB. Okay, so when we're back here, BB is exactly twice the length of A, so it's just recycling A, and we end up with exactly the same thing that we had here. Okay, but again, this is probably undesirable for our function because it's unexpected, right? And if we don't understand the concept of recycling, then we would probably look at that and think that's a wrong answer, right? This will not work if they're not divisible. Okay, so here I have 1 through 3 and then AB, and I get this error and it says arguments imply differing number of rows or something like that. Okay, so it doesn't work if they're not divisible, but if they are divisible, then it'll do that recycling. So in the both NA function, recycling leads to unexpected results. So what do? Well, one thing we could do is before actually doing that operation, we could check to see if they are the same length. If they're not, we could return an error. Okay? in R, when you're writing functions, you use stop to throw an error. Okay, so there's other variants like stop if not, which we'll talk about in a minute, but stop is the general way that you're going to throw an error. Okay, so basically the function is going to be going through, and then you're going to test a condition, right? If that condition is met or that condition is not met, whatever you decide to do, then you would say stop, and then you would give some error message. Okay, this is the basic structure. So we have both NA, we have a function x and y, and we're going to say if condition stop, and then whatever the message is, and then we're just going to go on from there. So this is an example where we have an if, but we don't have an else. Okay, and that's because we're going to test this condition, but then it's just going to move on after that. Okay, so if this condition is false, it's just going to skip over this whole thing and it's going to continue on with this. And stop will actually stop the evaluation of the function, so it won't continue on to do this stuff anyway if this condition is met. Okay, so here's my challenge to you. Modify this code below to A, put in a condition that actually works here, and then B, includes a message that is actually meaningful. Okay, so we've all experienced times where you do something and you get some error message that is completely indecipherable, right? It makes no sense. So that often happens, and I have errors in my own packages that are like that, unfortunately, but that often happens because you're running into things where it's like you're not catching it here, and so then it's running into all this other stuff, and then you get some obscure error message. So what you want to do ideally is catch it before it goes down that big long line, and then throw a meaningful error message there. Okay, so copy this code, try to write the condition that will make it go into this part of the function if that condition is met, and then write a stop message that's meaningful. Okay, 2 minutes, give it a go. Okay, this is how I would have done it. Okay, I would say if the length of x does not equal the length of y, then we're going to go into this part. Stop, vectors are of different lengths. Okay, and then otherwise it's just going to continue on, and we're going to do this part. Okay, so if we say both NA, A and B, we get 2. If we say both NA, A and BB, then we get error in the call. Vectors are of different lengths. Okay, did you do something like that? Okay. Okay. Can we think of something that would make the error message even more meaningful, though? So saying they're different lengths is good, but could we do something that's even more meaningful? We could state the lengths of each of them. Okay, so rather than just saying these two generic vectors are not the same length, we could say the first one is length 7 and the second one is length 14. Okay, so now we'll do it like this is how I would do this one, right? The condition is going to be the same as before, but now within this condition, so if this is not met, I'm going to first calculate something I'm calling v lengths, okay, the vector lengths. And then these arguments are called x and y, so I'm just going to pass those here too. And then I'm going to say paste 0, x is equal to the length of x, and then comma, y is equal to the length of y. Okay, and then for my stop message, I would say vectors are of different lengths, and then v lengths. Notice in my stop message here, I'm putting this together just like I would paste, right? Just like I did up here, but I don't actually have to use paste within here because stop will put them together on its own. Okay, so I say vectors are of different lengths, and then I put this v lengths thing here that I've calculated. So now when I say A, B, B, then it says vectors are of different lengths, x equals 7, y equals, and it's running off the screen, but 14. Okay, that make sense? So then this is telling us when we're doing this, this vector is of length 14 and this vector is of length 7. Questions? Okay. So sometimes we want just quick error messages. Okay. This is pretty unusual, I would say, for me. But occasionally it's more like when you're doing interactive work, right? And I'm doing something and I know if it's not numeric that I need it to just stop. Okay. So what you can do then is use stop if not. Okay. So again, this is like not super often that I use this. It's usually when I'm writing just sort of a one-off function that I'm going to use for myself. But here's an example with a z-score function. Okay. So I'm saying stop if not is dot numeric x. Okay. Otherwise, it's going to continue on with this. So if I say z-score on ABC, then it just says error in z-score is dot numeric x is not true. Okay, so it's just basically echoing this part of the error and it's saying that's not true. So therefore, I'm going to error. Okay, and if I say z-score on these 3 values, then I get those. Okay, so that's just another alternative. I'm mostly showing you that because you may see that out there in the wild, but generally I don't use that one much. Okay, warnings. Warnings are just like error messages, but instead of using stop, we're going to use warning. Okay, other than that, it's the exact same. So this is a very tricky challenge. That's why I've given you 6 minutes here. Okay, but what I want you to do is take that prior code that you have and modify it so it runs but returns a warning if the vectors are recyclable. Okay, and if they're not recyclable, then it returns a meaningful error message. Okay, so you'll need 2 conditions, one to check if they're recyclable, and then one to what was it? One for the warning and one for the error, basically. So one to check if they're recyclable, and then if not, you're going to error out. Okay, so check if they're the same lengths. If they're the same lengths, check to see if they're recyclable. If not, throw an error. If so, throw a warning. Okay, so you'll need 2 conditions, and then this is the other code that I'm giving you that is very helpful for this sort of task. Okay, this is called the modulo operator or modulo division. So this is going to give you the remainder. Okay, so if I say 8%, 2, and 8%, 4, then it's going to give me 0, right? Because there's no remainder. 8 divided by 2 is 4, there's no remainder. 8 divided by 4 is 2, there's no remainder. But if I say 7, : 2, it's going to return 1, okay? Because that's the remainder, right? 7%, 4 returns 3. Okay, does that make sense? So if you divide the thing, whatever the remainder is, that's what it's going to give you. So if you want to check if something is recyclable, basically you can use this modulo operator and you should expect that it will return 0. If it returns 0, then you're good. If not, then they're not recyclable. Okay, so this second hint is what you're going to do to try to figure out if they're recyclable. And then this first hint is just you're going to have to figure out how the error messages and warnings go. Okay, so I'm going to give you 6 minutes. Try to build the function so that it does all of this stuff. Okay, ready, go. All right, got a lot more of a mix on this one than before. As I said, this one is quite tricky, so I wouldn't necessarily expect that you would be able to do it, but I'm very happy if you were able to do it. It's pretty tough. This is how I did it, okay? So we do have 2 conditions, but part of what's tricky here is that the condition is within the condition, okay? So first thing we're going to do is just check if the lengths are not equal, okay? If they're not, then we're going to go into this, but notice that this extends from here clear down to here, okay? So all the rest of this stuff is only going to happen if the lengths are not equal, okay? So let's assume that they're not equal. Then I'm going to calculate the length of x. I'm going to calculate the length of y. I'm going to create this v length thing that is the same as I had before. But now I'm going to say if Lx, so the length of x, percent, right, the medulla thing, Ly equals 0, or Ly percent, Lx equals 0, then we're going to throw this warning where we're going to say vectors were recycled, and then I'm going to put the lengths of the vectors. Okay. Else, so if instead of this, and again, this should be up here. I'm not sure what's going on here. But so otherwise, if the lengths are not equal and this condition isn't met, then we're going to say stop. Vectors are of different lengths and are not recyclable. Okay. And then I state the vector length. Okay. So then if none of that is met, right, then of course we're just going to do this part. So this is now quite a bit of code where really the only code is right here, right? The rest of this is just checks for different things and returning warnings or errors. So we can test it out both in A and BB. We get a warning both in A and BB, but I'm removing the first element of this one, and we get an error. Vectors are of different lengths and are not recyclable. Okay, so step back from the ledge for a second. Sorry, I'm getting a call. How important is all this, right? For most of the work you do, probably not very, okay? I'm showing you this for kind of two reasons, right? One is just sort of exposure to get you to think about this stuff a little bit. And the second is if you do decide to go on to do things like develop a package, then it is actually pretty important, right? If you're not developing an R package, then this stuff is really not that important and not something I do unless I'm writing a package, basically, okay? I might do that stop if not. I might occasionally have something where I'm doing a warning just so I'm giving myself a message if something is happening. But generally, I'm not going to do it except in my package development stuff, okay? If you're developing functions that other people are using, so let's say you're writing a paper with somebody and you're just sharing your script with that person and they're going to be running the analysis. Also, maybe you're doing part of it and they're doing a part of it or whatever, and they're going to be using your functions as part of that, then it's sort of important. And like I would personally probably tend to try to err on the side of including more of these things because it's not going to hurt you necessarily, but it could be helpful. But that person could always just come back to you too and be like, what's going on here? And you could talk them through it or whatever. So this is sort of the gray zone where it's like, yeah, maybe you do it, maybe you don't. If you're just doing interactive work for you, I probably wouldn't do this stuff most of the time. Okay. If you are developing a package, then it's quite important. Okay. So if you don't feel like comfortable with this at all, and you don't feel like you could write that at this point, that's okay, right? That's fine. At least you're getting the idea that this is something that you might want to do at some point down the line. Okay? Does that make sense? Okay. All right. The last topic for today is return values. I also realized we never actually talked about messages here, but the tidyverse in particular is very message heavy, right? So like when you load, you say library tidyverse, and you get that big message that says what packages are loaded and the versions of all of them and everything like that. And then like ggplot, if you do a histogram, it will always be like bins equals 30. Please choose a better number of bins or whatever. Those are messages, and those are, you create those the same way that we do with the warnings or the errors. You just use message instead of warning or stop. Okay, so if you want to do something like that, you could. All right, return values. So by default, the function will always return the last thing that is evaluated. You can override this behavior with the return function. Okay, this is part of what you can do to allow your function to be conditional. So if something happens, then you're going to return some output. If something else happens, you'll return a different output. Okay. Generally, the last thing that's evaluated should be the sort of default for your function, or the most common return value. Okay. So real quick, pop quiz. What will this return? Nothing. Why? Any ideas why this is returning nothing?
Because you're saving the result variable, but not like printing it or anything afterwards.
Exactly. So we are storing the result of this to result, but we're not actually returning the result. We're not saying this is the thing that should be printed, right? And actually what's interesting about this is if we had stored this to an object, that object would contain the result actually, but it won't print it to the screen. Okay, this function will never print the result to the screen. So that's generally not what we want to do. All three of these are the exact same thing. Okay, they're all equivalent. So here we have the same function we had before, but now we're just saying and return result, right? Here we just get rid of this whole assignment operator part and we just say it's x plus 2. That's what we're going to return. And then this last one is the most explicit. We're creating an object called result, and then we're saying return result. Okay, and again, there's nothing wrong with that at all, but generally you want to reserve that return function for sort of non-standard return values. Okay, so otherwise, so basically I would not do this one generally. Okay, I would probably do one of these two, and if it were this simple, I would just do this. Okay, but very often I'm doing something like this too. Okay, thinking about function names. All right, I don't know why this is in here, but whatever, it's an important topic also. Look at these three functions. These three functions are all the same thing. They're the exact same thing. But which of those is the most intuitive? It's the last one, right? Because this is just f. That's not helpful at all. This is p-tile, and it's returning a percentile, so that's nice. But it could be better. And this one's percentile underscore df. So this one's by far the most descriptive because it's going to return the percentiles for some x variable, and it's going to return it as a data frame. Okay, so and then we could actually make this even better by changing the output a bit so that it returns what x is called. So this is a little bit tricky, and again, this is not like something that I would necessarily expect that you would do, but it is sort of a nice way to handle things. So I can use this match.call, I change it as a list, and then I'm calling this thing arg. So whatever I pass this thing, it's going to end up in arg. Okay, and then I'm just changing the names of the first thing in x to be the names of that arg. Okay, and the reason I do that is because now I end up with something like this. So I'm creating a random vector here, and I'm calling rnorm 100. Okay, so here it's giving me the percentiles for all of those values, but the name of this thing is random vector. It's the name of that thing I passed it. Okay, so the return value in this case, the data frame, has properties that make it more intuitive based on its input. Okay, so that's a nice feature. Here we say rnorm 50, and it's going to take this argument and it puts it in a sort of nicer form like that. Rnorm 50, that's the name of the thing, and then here's the corresponding percentiles. Okay. All right. The other way that I use return very often is to debug functions. Okay, so I might have some function that I've written and it's not working and I can't figure out why, right? That's where I would use return to actually stop the function at a certain point and return it at that point, and then I can look at what the function is outputting. Okay, so real quick, I'm going to actually go to R and show you an example of this. If I can get my share to work. Okay, so here's an example of a function that is currently not working. Okay, it takes three, it's called report means. All right, it takes data, group, and X arguments. Okay, and what I want it to do is basically take that data, and then I'm going to pass it a grouping variable, and then X, which is the variable I want it to summarize, and then I want it to give me a message in return that says, here's the means for that thing. Okay, and I'll be honest, I don't even know if we'll be able to debug this in time, because I just kind of wrote this quickly and we only have like 5 minutes left, and I know it wasn't working. So I don't know what's going wrong with it yet. I do know part of it, what's going wrong, but we'll see. All right, so here's an example. We'll say report means, this is a function that, so I'll run this, right, just to make sure it's that way. Report means, we'll go with empty cars because it's easy. We're going to split it by cylinder, right? And then I want the MPG, right? So if I run that, it says error in split.default, group length is 0, but data length greater than 1. So it's like, okay, well, that's not very helpful. Maybe I can return split. Okay. Now, when I do this, I still get the same thing. And then I look at this a little closer, and it's like, oh, yeah, well, I'm trying to split it by that. That's not going to work, right? So what I need is this to be there, which means this thing is going to have to be like that, and that is 2. Okay, so let's try this again. So that was more an error on the way that I was writing the function. And all right, there we go. Now I've got the split. Okay, so that part's working. So the split is working. Now I'm going to take the names of means. Oh, see, this is part of the problem. I'm saying names of means. I need this to be names of split. So I can change that right now. And then let's just have it return names and make sure that that works. Okay, and it does. Okay, so we've got 4, 6, and 8. That's names. And split is our split object. We know that's working now. Now let's see if means works. So means, we're going to v-apply for split. So we're going to loop through split. I'm going to apply this function group, where I'm going to say, give me the mean of group X, right? So X is MPG. I think that should work, but let's just check to see if means is giving me what I expect it to be. All right, it is not. Oh, fun.value is missing. All right, so that's good. So now I need to say fun.value is equal to double 1. Okay, now we'll rerun that, and there's our means. Great, so we're good there too. Now the last part here is I don't have to use return, because this is the last thing. I usually put a little bit of a space here to sort of separate my return from everything else. But now I'm going to paste 0. I'm going to paste the names, colon, space, and then the means. Okay, and then I'm going to cat, which means it's going to just print it to the frame, to the data frame without any quotes or whatever. And I'm going to collapse with an n, which means a new line. All right, so I think this should work now. And it sort of does, but probably not exactly what I want. So I'll say round this to 2 decimal places. And then I'm not sure why. Maybe I need to say paste like that. And then maybe that'll work. There we go. That's what I wanted. Okay, so now I have 4, 6, and 8, and here's the means for each of those. Okay, we could try it on a different one just to make sure. So we'll go Palmer, penguins. We're gonna, let's say we'll group by species. Okay, we'll group by species, and we'll compute the mean for flipper length millimeters. And there we are. There's the means. Okay, so that's an example of I had a function that wasn't working, and it truly wasn't working, right? I wrote that like 1 second before starting class, and it wasn't working, and I couldn't figure out why. And then using that return value over and over again, we can kind of pull out pieces of the function, and then we can build up until we're like, okay, now the function is working, and we tested on a couple of different ones to make sure. Okay, does that make sense? Okay. And then other than that, the other reason we would return different values is, like I said, if we have things like maybe we want to return a data frame or a vector, and you can let the user decide which one they want to return. And you'll say, if data frame equals true, then return data frame, right, of your stuff. And then else it would just be the vector. All right, last thing I wanted to mention is in the approach I just used, right, I use just base R stuff. Generally, that is how I try to approach things because I don't want dependencies. Dependencies, though, are not the worst thing in the world. The only problem with them is that they can make your functions break. So if you are using something from somebody else's package, and then they change the way that that function behaves, suddenly your package doesn't work because they made changes, right? So that's a dependency, and that's problematic. So if you're writing a function that's just for you, I wouldn't even worry about dependencies. Just get the function so that it works for you, right? If you're writing packages, then you're probably going to want to worry about it a fair amount, okay? The other thing that you might consider is using namespacing like this, because that'll explicitly say this function is from this package, and it'll also help you avoid conflicts. So like dplyr filter and mass filter, right? Those are two functions with the same name, but from different packages, and they do different things. So if you say dplyr : filter, it'll always use the function from dplyr. All right, so that's basically it for today then. So on Monday, we will have our third and final lab. We will also review the midterm then. Okay? The lab is actually already posted too, so if you want to go and check it out between now and then, you can. All right? Any last minute questions? Okay, thank you all. I will see you next week.